Have you ever wondered how Java achieves its write once, run anywhere paradigm? It's all thanks to the semantics of bytecode and the power of the Java virtual machine. But how does it really work behind the scenes? Let's uncover the secret that makes Java both universal and efficient. So what exactly is bytecode? Think of bytecode as a middleman. When you write Java code, you save it in a .java file. But before the computer can understand it, the Java compiler converts it into an intermediate format called bytecode stored in .class files. This bytecode is platform independent, meaning it's not tied to any specific hardware or operating system. Bytecode can be interpreted by any Java virtual machine, ensuring that your Java program runs consistently across different platforms. For example, if we compile this hello-world.java file, it generates a file called hello-world.class. That's the bytecode we're talking about. Now let's talk about the Java Virtual Machine, or JVM. The JVM is responsible for translating bytecode into machine code that your specific device can understand and execute. It's the translator that takes the universal bytecode and adapts it to the architecture of your operating system and hardware. It's fully multi-platform. You have Windows, macOS, or Linux all running the same Java app. This is how Java achieves its famed portability. No matter where you run your code, the JVM ensures it runs the same way. Let's break down how the JVM works in 3 main steps. First, the class loader loads the bytecode into the JVM. It organizes and links the code, making sure everything is in place. Before running the code, the JVM verifies the bytecode to ensure it's safe and doesn't break any rules. This prevents your system from running malicious or incorrect code. Finally, the bytecode gets executed. This involves the just-in-time compiler, which translates bytecode into native machine code for faster performance. Initially, when a Java program runs, the JVM interprets the bytecode one instruction at a time. This means it reads the bytecode and translates it into machine code on the fly, which allows the program to start executing immediately. However, interpreting bytecode one instruction at a time can be slower compared to running directly in native machine code. This is where the just-in-time compiler comes in. The JIT compiler analyzes the bytecode as the program runs and identifies the section of code that are frequently executed, often called hotspots. Instead of interpreting these hotspots repeatedly, the JIT compiler compiles them into native machine code during runtime. This means that for these frequently executed parts, the JIT compiler turns the bytecode into optimized machine code, which can be directly executed by the CPU, bypassing the need for further interpretation. As a result, once the JIT has compiled these critical sections, the program runs much faster. Here's a quick example. Let's say we write this simple Java program. This program defines a class called hello world with a main method, which is the entry point for any Java app. And inside the main method, it calls system.out.println, a built-in function that prints the string hello world to the console. When compiled, the .class file contains bytecode that looks like this. This is what the JVM reads and executes. Bytecode is a platform-independent, low-level representation of Java code that can be executed on any system with a JVM. The JVM interprets or compiles this bytecode into native machine code, ensuring that Java applications run consistently across different platforms. The JVM also handles memory management, garbage collection, and runtime optimizations like just-in-time compilation, making Java efficient. It provides a secure execution environment by enforcing access control and verifying bytecode before execution. Thanks to bytecode and the JVM, Java abstracts away platform-specific details, which ensures that applications are portable, secure, and efficient across any environment.